Hello, everyone, and welcome back to Data Platform Week, and thank you for joining us today. Yesterday, Nick Schrock, founder and CTO of Dagster and co-creator of GraphQL, took us through the challenges of building a modern data platform and how teams are approaching it. Already saw someone ask in chat for some of the slides from that, so we'll be posting those up at the end of the week, and hopefully you can use them and they're helpful for you. Today is an exciting day filled with all things orchestration and event-driven handling through declarative automation. We have 3 exciting sessions planned for you today. We're going to start off with a great session from Owen Kephart, a software engineer at Dagster who has been one of the major driving forces behind the development of declarative automation. He will take us through common scenarios that data practitioners are encountering and how you can harness the declarative automation framework to help simplify some of these challenges. After that, we will jump into 2 amazing end user talks from Enigma and Kahoot. So more on that later. Just some general housekeeping notes. We will be answering questions after all 3 talks are complete. You can use the Q&A button to ask your question at any time, and some of them may be answered via chat. Some will probably be answered on mic at the end. So just please use the Q&A feature so that we make sure that we don't miss any of your questions. And without further delay, Owen is going to take us away here. So thank you, Owen.
Hi, my name's Owen, and I'm a software engineer working on Dagster. Today, I'll be walking through Dagster's new declarative automation system and how it can optimize how you update data across your entire data platform. If you're a longtime Dagster user, this system builds on the original auto-materialized policy abstractions to create a system that's more flexible, more predictable, and easier to use. But before we get into all that, let's talk about some of the challenges data teams encounter with other automation methods. Data platforms are often incredibly complex. Organizations can have hundreds or thousands of distinct data assets owned by a variety of teams. These assets typically exist in a complex structure of dependencies, where the status of any upstream asset can impact the decision of whether or not to execute. Crucially, you often have no direct control over those dependencies. They might be handled by another team or a completely external system. If upstream data is slow to update or never arrives, that has a direct and cascading impact on when downstream assets should be run. Historically, data engineers have worked around this in a variety of different ways. The simplest solution is to set up cron schedules at offset start times. So the first stage of your pipeline might run at 9 a.m., the next at 10 a.m., and so on. The core issue with this solution is that it ignores important dependency information. We know that the second stage needs to be run after the first, but because this link is not encoded anywhere in the system, upstream failures don't prevent downstreams from executing. The net result is that incorrect or incomplete data propagates through the rest of your data platform. This scheme is also an organizational liability. It becomes the role of documentation or siloed knowledge to keep track of the proper sequencing. This means that detecting these issues is inherently a manual process and makes debugging them a massive challenge. Another option is to group all of your assets into large, cross-cutting jobs that span team boundaries. This tight coupling ensures that upstream failures prevent downstream executions, but removes the ability for teams to operate independently. In essence, it couples together the outcomes of all assets in your graph together. Failures or slowdowns in one part of your data platform can impact unrelated computations that have been grouped together for convenience. This scheme also quickly breaks down as soon as you have assets that need to run on different cadences. Once again, you need to contend with dependencies between individual jobs. Something as simple as having a core set of assets run daily instead of hourly causes problems, as the more assets you lump into each job, the more potential dependencies you have between those jobs. Solving this issue often incurs further compromises, with a common solution being to simply give up and run more assets at a higher frequency than necessary, just to avoid confronting these interwoven dependencies. All of these workarounds impose a massive tax on productivity. While it may be simple to express and understand the behavior you want, implementing this behavior using imperative methods is generally too challenging to be practical. This impedance mismatch raises costs across all dimensions of a data platform. Slower dev cycles, more time spent debugging, less timely data, lower data quality, and wasted cloud compute costs can all be traced to inefficient and inaccurate automation methods. We believe that there's a better way. Dagster already provides a unified view of the dependencies and statuses of assets in your data platform. Why not use this information to make intelligent automation decisions? Declarative automation is Dagster's solution to do just that. It provides powerful, composable abstractions to describe when you want assets to run, as well as pre-built combinations of these building blocks to ergonomically handle the most common use cases. The result is an intelligent, event-based orchestration method that allows you to define when individual assets should be executed in a way that incorporates fine-grained information about the status of your data platform. From there, the system takes care of the complexities of monitoring that state and launching runs in response. This represents a new paradigm for automation, which treats the asset lineage graph as a key building block and allows you to tap into Dagster's wealth of information without any complex custom code. To make this more concrete, let's get started with an example. The first step in most data pipelines is to take some raw data and process it. For this example, we have raw event data that's uploaded to S3. This is done by an external process approximately once an hour, but the exact time isn't always consistent. We can track these updates using Dagster in a couple of different ways. We could pull the S3 bucket listening for updates, or we could have an external process send events to Dagster using our REST API. Either way, we want to get this data into Snowflake as soon as it's available, and then start processing it with our dbt project to make sure that stakeholders can see the updated data as soon as possible. A regular cron schedule just doesn't work here, as there's no specific time at which we can kick off our downstream computation that'll guarantee that our upstream data will be ready. We need to explicitly wait for that upstream data to come in. Dagster provides a built-in eager condition that you can attach to your assets and will handle this scenario, updating your asset directly after any of its parents update. To emphasize, Dagster already knows what data each asset depends on, and so there's no need to explicitly redefine this anywhere. All you have to do is say, update this asset after its parents update, and Dagster will know exactly what that means. This condition also bakes in a few common sense extensions. For example, if another upstream is currently in progress, it'll wait for that upstream to complete before kicking off, which reduces unnecessary computation. Again, Dagster has knowledge of both the dependencies between your assets as well as the status of them, and is able to use this information to intelligently react to events. Now, if we go to one of our Snowflake assets in the UI, we can see a detailed history of whenever it was or wasn't automatically materialized, as well as the specific reasons for this decision. The built-in eager policy is a combination of simpler conditions. When defining your asset, any of these conditions can be modified or removed to handle more specific situations. We can drill down into the specifics of why this asset was kicked off at this time, making it possible to understand the exact inputs that went into every automation decision. This precise explainability means that you never have to wonder why a run was or wasn't kicked off. Now that we've set up our data to be automatically processed and cleaned, we'll want to do something more interesting with it. We have a downstream machine learning team that takes this processed data and uses it to train a predictive model. Retraining this model whenever we get any new data would be unnecessary and would be far too expensive. We just need to update this once a day, but only once its upstream data is ready. To do this, we can use another built-in condition, on cron. You can think of this as a more intelligent cron schedule. Rather than kicking off immediately on a cron schedule tick, it'll wait to make sure all of its upstreams have been updated before moving on. No matter how many times the upstreams update, an asset using this policy will still just update a single time per day. And if some upstream data never comes in, then no run will be launched at all. This means that we don't need to create any imperative workflows or coordinate with the upstream core data team at all in order to schedule this asset. We simply tell the system how this asset should be updated, and it'll wait for the right time to kick off. To reiterate, when setting this up, all you need to think about is the cadence you want this asset to run on. You don't need to think about how to organize this asset into a job or how and when the upstream assets are getting updated. Each team is free to modify and optimize their assets without having to make large, team-spanning changes to keep everything in sync. By using this declarative model, we've avoided the pitfalls of traditional solutions. Cross-team dependencies no longer incur organizational costs, and setting an asset's cadence no longer needs to be a trade-off between cloud costs and complexity. So, to take a step back, the features you've just seen already represent a huge step up over the alternatives, but we've just scratched the surface of what's possible with declarative automation. Let's touch on another area that's traditionally challenging to manage. If we recall the original premise, we have some external process that drops the previous hour's worth of data into an S3 bucket. In many cases, it'd be useful to understand the status of each individual file, rather than treating the collection of files as a single unit. Similarly, we may want the ability to look back at the model training runs that we executed each day to understand how it's changed over time. We call these sorts of assets that operate over distinct slices of data partitioned assets. From a modeling perspective, Dagster makes it easy to represent these sorts of assets. All you need to do is apply a partition step to your asset, indicating how this asset's data is logically partitioned. In this case, we could partition the top part of our graph by hour and our machine learning model by day. Once that's done, we can see the UI update to track these partitions individually. From here, we can kick off runs of individual partitions or backfills of larger time ranges. But this higher fidelity modeling exposes new scheduling constraints. If we have, say, a daily partitioned asset downstream of an hourly partitioned one, you'd like to make sure that all of those hourly partitions are filled in before you kick off your downstream asset. It's not enough to just track the most recent upstream update. You need to have a full understanding of each individual piece of upstream data in order to automate this asset correctly. In legacy orchestrators, this sort of dependency would be a nightmare to track, let alone use to make scheduling decisions. But in Dagster, this all happens with no extra effort. You don't even need to update your automation conditions. These conditions are partition aware and understand not just the dependencies between assets, but the dependencies between partitions of those assets. So if your upstream data fails to get updated for a few hours, you don't need to worry about downstreams kicking off with incomplete data. And as soon as that upstream data gets filled in, downstreams will kick off again. These partition mappings can get arbitrarily complex, but the core condition determining when an asset should be kicked off remains identical, regardless of what those dependencies are, meaning no custom logic needs to be added. Encoding and understanding this dependency information is essential, and declarative automation makes this easy. Finally, throughout this presentation, I've spent a lot of time talking about updating data assets, but that's not the only sort of computation that can benefit from deep knowledge of the status of assets and their dependencies. Historically, managing data quality has been a challenging thing to nail down. Of course, everyone wants to make sure that the data that goes through their pipeline is high quality, but this requires additional computation in order to determine if the data is high quality or not. This poses the question, when do we run that computation? Because data quality checks monitor the status of assets, they inherently exist in the same complex graph of dependencies as the rest of your data platform. Executing checks in the same pipelines as your assets can slow down or interfere with the core updates that you care about. But executing checks independently runs into familiar challenges as well. How do we make sure they only run after the asset it's monitoring updates? What if the check is expensive and needs to be run less frequently than the underlying data? These are the exact same challenges that asset orchestration runs into. The correct time to run these checks depends deeply on the upstream data dependencies. This means that in typical orchestration frameworks, these sorts of fine-grained decisions for these computations are generally too challenging to implement and force users to gravitate to the same simple but suboptimal patterns. Declarative automation removes this trade-off. It can automate checks in exactly the same way that it automates assets. Checks that should always run when their asset updates can have the very same eager condition that we use for assets, and checks that need to run at a lower cadence can use on cron. And again, more specialized use cases can take advantage of the full range of flexibility that declarative automation provides. For example, you can set up checks to only run when the asset they're monitoring changes its definition, or put a rate limit on how often a check can run. Wrapping things up and zooming out, we've talked a lot about the challenges that traditional orchestration frameworks have with common everyday situations. We would argue that the reason for these challenges is that we've been using the wrong tool for the job. A tool that doesn't understand asset dependencies and their statuses fundamentally cannot effectively orchestrate even simple dependency structures. The result is wasted cloud compute costs on runs that never needed to happen, wasted dev cycles trying to implement and debug patchwork solutions, and data that's less timely and harder to trust. Declarative automation presents an alternative: simple, ergonomic APIs that make the common cases effortless, combined with the flexibility to handle any specialized needs. We're excited to have you try this out and see what it can do for your data platform.
Wow, that was awesome. Owen, thank you for the great insights into declarative automation usage and some helpful tips about partitioning as well. I think it's always a great opportunity to get to hear directly from like the engineering folks that are building these features out. So this is really a good opportunity for you guys to get your questions out there. If you have features that you want to see or just hearing about your use cases is incredibly valuable as well. So thanks again, Owen, for that. And that also sets us up really nicely. It's a good segue into our next talk, which is from Tien about orchestrating SMB data. So Tien leads a phenomenal team of engineers and data scientists at Enigma, where he is the overall tech lead for the data platform infrastructure. So thank you, Tien, and yeah, please take it away.
Hello everyone and welcome to the talk Orchestrating SMB Data. My name is Tian Xie and I am a Director of Engineering here at Enigma. I've been here for soon to be 7 years and I am currently the tech lead of the data infrastructure team. To provide some background on Enigma, we provide data on SMBs, which stands for small and medium-sized businesses, or companies with up to 100 employees, including tech startups. We collect data from hundreds of public and third-party vendors and resolve those different and disparate sources into a single, rich dataset that provides insight into the identity and financial health of those businesses. Our data empowers our customers to reach their target market, validate the legitimacy of a business, evaluate underwriting risk, and I'm probably forgetting a couple other things, but that's not what we're here to talk about. Enough boring business stuff, let's talk tech. Our data pipeline is written in Python or Spark SQL, which we host on GitLab and run on Databricks using either PySpark or Databricks Photon, respectively. Our data is stored on LakeFS, which is backed by S3. And of course, for orchestration, we use the reason we are all gathered here today, Dagster. One of the main reasons we were initially attracted to Dagster were to solve problems with testing and development. We were taking too long to release new features. And this was directly a result of how difficult it was to test changes to our data pipeline. As I'm sure is the case for many of you, our data pipeline runs in DAGs, directed acyclic graphs. Now, testing a single step in a DAG is fairly straightforward. You run that step, probably without any orchestration at all. But then, how do you test multiple dependent steps? In that case, you need a staging environment. But then, what if multiple developers all want to work on different parts of the DAG at the same time, and some are working upstream of others? A developer working upstream may change an asset in the staging environment, which confounds results for all downstream developers. It's likely possible that each developer can run each individual task manually, meticulously changing the outputs of a unique namespace and changing downstream tasks to read inputs from those unique namespaces. But this is too painstaking to describe, let alone use or scale. Of course, there are also cases where multiple developers may be working on unrelated changes to the same task. Eventually, we realized that we needed a way to create a sandbox DAG on demand. When the developer needs to test the pipeline, he or she creates a new sandbox environment and duplicates the entire pipeline. Once testing is complete, the sandbox environment is automatically cleaned up. This brings us back to our stack. Our stack enables us to create sandbox environments for a branch of changes on demand. I presume all of you are already familiar with Git. Of course, GitLab allows different developers to work on different branches of code. Nothing new there. Now, Dagster enables branch deployments of the data pipeline DAG. And LakeFS enables branching our entire data store. Meanwhile, Databricks provides an execution layer that works for any branch. And all this together allows different developers at Enigma to work on changes to the data pipeline without even thinking about what environment am I using, or am I blocking someone else? It doesn't matter. Just create a new sandbox and keep iterating. This stack made our developers' lives easier and improved our iteration speed. Now, this is all great, but it's not actually what I'm here to talk about. It's Core Orchestration Day, so I'm here to talk about orchestration, which is the other major reason we use Dagster. But before I get into that, a little more background about our process. So we work on SMB data, and SMB data moves slowly. This is not high-frequency trading or real-time ad impressions. Our sources update monthly, and that's the general industry trend. Our customers also expect updates monthly. I mentioned before that we resolve different and disparate data sources into a single rich dataset. So, since our customers expect updates monthly, we run a resolution process of all of those different and disparate data sources into one enormous DAG on a schedule. However, our sources update monthly, but they do not do so all at the same time. Rather, they are staggered. Consequently, our pipeline consists of segments that are scheduled, the resolution component, and event-driven. That's ingesting new sources. So before Dagster, we were using Airflow. For event-driven workflows, this involved a sensor task that ran on a cron loop to check if a new delivery arrived. If it had, then the rest of the workflow ran. Otherwise, a run failed. This meant that loops in which there was no update appeared as failures. This was terrible. The cron loop ran constantly, so there were hundreds of false positive failures. These false positive failures were not easily distinguishable from actual failures, so it was very easy to miss bugs and forget about alerting from the orchestration layer. It was hard to even dig up successful runs. Now in Dagster, sensors are a native concept. There are sensor ticks that request runs, and then the success or failure to materialize assets requested in those runs are logged as events on those assets. All of this is much easier to sift through. I mentioned before that our sources update on a staggered schedule. I should also add that some of our sources are normalized across multiple tables. Different tables might also update on a staggered schedule. It's possible to download, tabulate, and clean each table as it comes in, but our process requires having a full set of normalized tables before we can transform or ontologize the entities into our ontology. This means that we need a mechanism to wait for all of the normalized source tables to update before proceeding with ontologization. In Airflow, this required writing a highly custom workflow for each of these cases. But Dagster has a native condition for when all dependencies have updated. I mentioned that we download, tabulate, clean, and ontologize each data source. I'm sure that same pattern is familiar with many others here. Those terms were actually taken directly from our workflows. We had steps named download, tabulate, clean, and ontologize. The name of those steps also correspond to the name of the functions that were called in those steps, which were shared across many data sources, tweaked with slightly different parameters. In Airflow, despite identical tasks, it was necessary to deploy a different workflow for each and every data source, meaning we wound up with hundreds of identical workflows, different only in name. Since in Dagster, though, the DAG is based on assets instead of tasks, so the need to deploy these different workflows goes away. Instead of coding tasks, you define the assets and the edges to transform between them. Once a source updates, Dagster will dynamically create a run that effectively replicates one of those workflows. So, for example, when asset A is delivered, Dagster will create a run that materializes assets A0, A1, A2, and A3. This effectively replicates the same workflow in Airflow, but importantly, you do not have to explicitly define that workflow. Now, so far, I have brought up orchestration when data changes. Upstream data asset updates, so then the downstream assets update. But what about code? When code updates, the downstream assets should also rematerialize. Dagster handles that. It is possible to specify a code version property for each asset. Technically, this property is an arbitrary string, but the intention is to set a value corresponding to the code used to materialize that asset. When an asset is materialized, that code version is recorded with the materialized asset. Then, when you deploy a new DAG, meaning you made some code changes, you deploy a new DAG, if the code used to materialize that asset has changed, then you should have a new code version. And Dagster has a condition to rematerialize the asset upon this property changing. This is an exciting recent feature from Dagster, and I'm proud to say we have just started to use it at Enigma. So that is all. Thank you for listening to this talk.
All right, so that was great. Thank you, Tian. We really appreciate you sharing your hard-earned knowledge on how you built your data platform with Dagster. I thought it was really interesting to learn about how you're leveraging the branching, but also declarative automation to batch and orchestrate your data. Uh, and I guess the other cool thing was, seeing how you utilize those sandboxes for testing. And I can definitely see that that would be a pattern that would be immensely useful for a lot of different companies and data teams. So thank you again for sharing that with us. Next up, we have Stig, and Stig is going to take us through how they leverage declarative automation and how they use it to help balance the urgency of various types of data requests. Stig is a data engineer at Kahoot, and he's responsible for architecting and building the foundational components of Kahoot's fairly massive data landscape. So let's go, Stig.
Good morning or afternoon, everyone. My name is Stig, and I'm a data engineer at Kahoot. And today I'm going to talk about how we're using declarative automation in the Kahoot data platform. But first, what even is Kahoot? We are a global learning and engagement platform company, most known for the quiz games called Kahoots, where users play quizzes around a common screen together. And some key stats about the platform include that since launch, we have hosted over 10 billion non-unique participants, that more than 8 million teachers have hosted a Kahoot during the last 12 months. And to give some context to data people on how much data this generates in the backend, our largest BigQuery table currently sits at around 62 terabytes. So to summarize Kahoot, our mission is to make learning awesome by creating engaging and impactful experiences for our users. And in order to reach that goal, you need data analytics, of course. So the data team's mission is to unlock value in our data to help make learning awesome. To look more into the data analytics, our data platform can roughly be split into two parts: the data lake and the data warehouse. And in the data lake, we interface against multiple data sources, services, and offerings used by different parts of the organization. This data is then stored in Google Cloud Storage in a high partitioning schema, which are again mapped to Dagster partitions, which enables us to represent the files in storage as big lake external tables that can be queried later. And in our data warehouse, we usually load data from the data lake or from tables made available from the Kahoot platform or backend. We then utilize dbt, managed by Dagster, to manage and build our data warehouse in BigQuery. Most assets in the data warehouse are either rebuilt daily or weekly and monthly for the more larger and heavy, expensive models. To look more into how we're doing declarative automation, I'll show you a simplified view of our lineage, which in broad terms can be thought of as the eager upstream world, consisting of API and data lake assets, and the lazy and punctual world with our data warehouse and marts and other end user models. While both worlds are owned by the data team, the eager part is maintained by the data engineers only. The other world, on that hand, we have some members in the data team that are also part of different functions of the organization, such as product, commercial, finance, etc. And they do a lot of work on serving the needs of their functions or teams by enriching or building additional models required by the business. Other stakeholders or teams in Kahoot can also leverage existing models in the data warehouse to create new analytical workloads or integrations or models for reporting purposes or, again, their business needs without having to rebuild models up from the ground again. The eager world, for the largest part, consists of observable source assets and raw and staging layer assets and the data lake assets. The assets are, for the most part, partitioned in a daily manner or non-partitioned, and the root assets will report data versions when a source changes for either the latest or the most recent set of partitions. When that happens, the raw and staging assets downstream will react and automatically materialize for the same partition, and the data lake asset will be updated to reflect that either new or refreshed data has been made available in the data lake. And due to a handful of different factors, we've seen that source data is often made available on an unpredictable basis. Either data is slowly consistent, which means that it might arrive a couple days late, or it's even delayed and not made available when it's supposed to. So configuring for daily scheduling has not been feasible in the past. So we just want to grab the data and add it to our data lake once it's been available in the source. In the lazy and punctual world, we have data warehouse models and end user models. These are structured according to the DBT best practices, with staging and intermediate and marts as primary layers, and additionally a selection of legacy models for analytical purposes. To declaratively orchestrate the materialization of these assets, our goals is to be able to set cron schedules for the end user models only, and then let the lazy upstream assets materialize based on those downstream conditions. And by that, I'm saying that we're only interested in setting a schedule for the exact assets that should be refreshed at a certain time, and then the rest of the dependencies should just follow suit. There should be no need to use the exact same schedule for the whole lineage in a graph, such as having an asset job with a schedule that selects and rebuilds the whole data warehouse on a schedule. So in order to make all of this work, we have defined a custom subclass of automation condition, which is a generic class which allows us to create or customize and reuse conditions that can fit our goals better. And you should note that we're still on Dagster version 1.8.13, which means we're implementing the subclass a bit differently than in the experimental feature introduced in 1.9, even though we'll upgrade to and probably use that functionality sometimes in the future. So for the conditions themselves, the first custom condition, missing or changed, evaluates to true if the partition is missing or the code version has changed. We're trying to make sure that we have code version as a metadata field for all of our assets. So when we deploy changes, the code version changes, and those assets should rematerialize to refresh the schema or refresh the data, whatever. So yeah, it's useful for materializing those kinds of assets. Secondly, we've derived our own eager condition from the default, with the possibility of also ignoring some upstream dependencies that have not been updated, or maybe they're simply missing. assets that we want to ignore are marked with a specific tag, which will include them in the selection of assets to be ignored. And this condition is useful when some upstream assets are unpredictably updated. In this case, it could be the observable source assets or the data lake assets, which update when the data changes in the source. Back from the old days, we missed the lazy so much that we decided to bring it back as an automation condition, which will evaluate the true if an asset is missing or changed, or requested by a downstream condition. And similarly to the good old auto-materialization policy, it's useful for cases where we want the materialization to be delayed until it's requested by a downstream asset. And the final condition we look at today is derived from the default on cron, which can also ignore that some upstream assets have not been updated since the previous cron tick of the condition. And we've also configured it in such a way that assets with a lazy condition will become triggered and materialized as part of the same run once this condition here evaluates the true. And this condition is useful for updating assets without really caring that much about the conditions of some upstream assets, while ignoring that some upstream assets might not have been updated since the last cron tick, which would have caused automation conditions hiccups and delay the materialization otherwise. Since most of the assets in our data warehouse are DBT models, we've, as per usual, subclassed the Dagster DBT translator to not only override how we want the asset keys, metadata, tags and such to be interpreted into our asset definitions, but also the automation conditions. And even though a lot of configuration can be done in code to define these assets, we want to keep most of the DBT specific parts in the model configuration files, and not necessarily in code or anywhere else. And by using the DBT props, which are just a dictionary representation of a DBT resource, we're able to map the configuration values into a Dagster automation condition for that resource. Therefore, we can say that these configuration files act as an abstraction layer where most, if not all, necessary properties are set, while the DBT translator acts as a kind of translation layer to map these DBT configuration values into the Dagster asset definitions. As an example of this separation, I'll show an example where we're looking at a model that has been configured with multiple automation conditions to materialize at 6 a.m. Every Monday or the first day of the month. This is a pretty common pattern to have data refreshed for analysis of the previous week or month. And we see here in the lower left screenshot that the conditions configured in the abstraction layer are ORed together to create a more complex condition. And this system is pretty flexible and enables us to build conditions based on different requirements. Finally, to wrap it all up, I just wanted to include a quote from our group's CTO at Kahoot. With Dagster, the data engineers are able to get the benefits of working like other software developers, at the same time keeping documentation up to date and being a lot more efficient due to the automation and lineage, which we did not have with our previous toolset. And Jostein has been following the data team and the data platform pretty closely for a long time, and he can definitely testify to the advantages automation conditions have brought forward for us to make sure that the data warehouse is rebuilt on time with fresh data and having timeliness and making sure that the data is available for reporting. And that marks the end of the presentation. Thank you for your time.
Thank you, Stig, and all of our speakers today, and all of our awesome attendees. It's always great to hear about concrete use cases and see the implementation details. I think many data teams are dealing with similar challenges, and seeing how you're solving them with Dagster is always fun to see. And informative for that matter. That actually concludes our content for day 2, but we do have plenty more coming this week. So just as a reminder on that, on day 3 here, which is tomorrow, we have Colton Patton's going to take us through the integration ecosystem around Dagster, as well as more information about pipes and pipes going into general availability. We'll have Jörg Heiler, who is from T-Mobile Magenta, as well as ASCII. He's going to take us through a cost-effective alternative to Databricks. And then Alex Noonan from Dagster is going to take us through embedded ELT and transformation. So that should be a great session. I mean, obviously, the integration ecosystem is extremely important to us. So make sure you attend to get more information about that. And then on Thursday and Friday, we're going to cover some other really interesting stuff. So on Thursday, we'll talk in detail about airlift and how you can simplify airflow migrations, as well as orchestration federation. We're going to have an excellent talk from Alex at Red Ventures on, which I think is amusingly named Changing the Car While Driving It, which will show us how he actually utilized airlift. And then on Friday, we're going to dive into data platform as a system of record, Dagster's data catalog, and get more information about that. And we're going to have a data engineering panel with Dagster, STF Labs, Sigma, and potentially another surprise guest on that as well. So make sure that you join us for those other days. We have a bunch of great content planned for each of those. And then I'm going to go ahead and kick it over to Q&A now. We have a ton of questions that have come in, so thank you so much for everyone for attending and all your great questions.
Awesome. Thanks, everyone. Yeah, we have several questions to go through. So I'll go ahead and read some of the questions, and then Alex, Owen, Tian, Stig, Nick, if you want to answer it, just speak up, and yeah, we'll go through these and address them. So right off the bat, the first question we have is there an auto-materialization rule to trigger when all upstream partitions ran, but some of them failed? And Owen, I think you might be most suited to address this one.
Yeah, absolutely. So one of the things that I didn't cover during my portion of the talk was the flexibility angle of these rules. So you saw a bit of that in the later 2 presentations, but one of the core ideas here is composability. So we can provide some out-of-the-box conditions that do what you want most of the time. But yeah, obviously there's always going to be custom cases where you have something that doesn't quite fit in that box. So underneath those built-in conditions that you were seeing me use, like eager and on cron, is sort of a tree of simpler conditions. So you can immediately detect, these partitions are materialized or these partitions are failed. And you can combine those with operators, so you can OR those together. And then you can also apply those conditions to the dependencies in the graph. And that's one of those like really powerful things about Dagster is you know the dependencies. And so you can like automatically apply conditions to dependencies. So in this case, yes, the short answer is yes, you can create a condition that says, all dependencies match, failed, or materialized. And that would do what you want there.
Nice. Thanks, Owen. Cool. I'm just going down the list. So next one is from Chris, and they said, do you support monitoring Airbyte upstream assets managed by Airbyte crons, or do you still need to move all automations to Dagster? So I think this is asking whether or not, if you don't bring your Airbyte assets into Dagster itself and represent them there, can you perform any automation on that? Owen, do you want to address this one too, or is there somebody else who might want to talk to it?
Yeah, absolutely. So again, one of the nice things about declarative or like asset-based automation is that it's defined purely in terms of that asset and its dependencies. So you are defining a condition on that asset that says, when something about the world is true, I will kick off. And that thing about the world can be made true in any number of different ways. So often, that'll still be declarative automation, automating those upstream assets, but it could also be, a traditional schedule in some completely external tool. It could be, people manually kicking off runs. It's anything. So as long as you have those Airbyte assets represented in Dagster and those materializations are coming in, then declarative automation will treat those materializations the same way as any other materialization.
Cool. In these materialization rules, can you call out to like external APIs, or is that not something that's supported?
So in 1.9, we have an experimental interface to allow you to write whatever Python you want. And so we have a lot of built-in conditions for detecting, failed, materialized, et cetera. But obviously, yeah, there are going to be cases where you need to pull in information from an external system that we won't have a built-in for. And at that point, you can use custom Python there.
Wow. Yeah, that's really cool. Thanks. All right. Next one is, are there ways to add failure alerts, and can they be sent downstream to alert the downstream teams that there were problems?
I can take that as well.
Sure,
Although
sure.
that is more of a that is Dagster Plus functionality that is available for you to use, just alerting in general. And we see that not as a declarative automation specific feature, but a feature that you might want to use for your entire data platform. So no matter what sort of failure is going on there, that alerting feature can help you there.
Yep, and you can use like custom sensors for that kind of alerting too, but it's much more seamless with the Dagster Plus version. Okay, cool. I'm gonna ask this one about LakeFS. So Tien, this one is probably best addressed to you, but does LakeFS have a backend like S3, or does it provide its own storage?
So LakeFS works with a S3-like backend. So you do need to set up some kind of object storage similar to S3. They support multiple different ones. I wouldn't be able to list it all, to be clear. I work at Enigma, not LakeFS, but LakeFS is a great product that we use. Yeah, they have different ones for Azure, Google Cloud, but I don't think they provide their own.
Nice. Yeah, so it's like a versioning scheme on top of your data on S3, which is
Correct. That's exactly what it is. Yeah, they provide the metadata on top.
cool. All right. Charlie asked, does declarative automation rely on the immediate upstream assets getting materialized, or could you program some logic that looks further upstream? In other words, could you skip over an asset materialization in the lineage? And I think, Owen, you kind of made this one relatively clear already that like the world's your oyster. You could create these like materialization rules that are extremely custom, and you could look at specific assets directly or anything like that. So I think most use cases are possible with the flexibility of declarative automation.
Yeah, that's exactly right. So there's any dependencies. There's an operator that applies a condition to dependencies. That operator can take in itself. So you can do whatever recursive magic you want, or look at specific assets. Yeah, again, the world is your oyster there.
Cool. And then this question, I actually think Stig and Tien could both talk to in their like real world examples, but Gaspar asked, how do you document all this using Dagster? So like, what is your documentation approach? And is that like documentation through code, or what are your approaches there?
I can go first. So we do a couple of different things. Firstly, we have a monorepo. So most of the high level definitions and concepts are simply described in README files in Markdown. We have some examples, we point to different modules and such, and we also try to document and have doc strings for let's say, as I showed the different conditions themselves, and if there are any DBT models that rely on those conditions, we try to also describe on a pretty high level how we want those assets to behave, so that we have a certain expectation if something goes wrong, or someone is trying to look into the documentation on how it works. So that's one way of doing it.
Cool, thanks, Stig. What about you, Tian? Do you have any suggestions for documentation practices?
Honestly, for much of our documentation, I feel like the Dagster UI is fairly useful for just say, for example, figuring out why did an automation condition fire up? You can look at the event and see what happened. In cases where it's more like, why are the rules for this asset set up in this way? We will usually have something that's written part of the metadata for that asset in the description or something like that. Just a human explainer of why that's way. But also we don't have super our assets tend to fall in a handful of categories in terms of what rules they use. So we don't have a lot of super custom rules for particular assets. So for the most part, that's what we've relied on. Yeah.
Nice, thanks. Alex, I'm curious what your take is on this one. A user just asked about using factory methods to dynamically create many assets. And the question is just, what's your opinion on that approach? Is that something that you're fond of, building factory methods? I know our documentation shows a few ways of doing that. Yeah, so I'm curious what you think.
I mean, they're useful if you have a like comment pattern that you need repeated a lot of times, so you're not rewriting the same code over and over again. And yeah, I think we've used them before. Colton, in your deep dive with Modal, you utilize asset factories. So
Yeah.
folks that are curious about like what that looks like in implementation, you can go to the repo for that, as well as the YouTube video where you explain it in more depth.
Yeah, I'm personally very fond of them. I see, Tian, you've raised your hand too. Do you want to talk about factory methods?
Yeah, that's exactly what we do. We have a lot of factory methods for generating assets. I mentioned in my talk that we have the download, parse, and so on. We have factory methods for generating a lot of assets that fall into those different categories. Yeah.
Well, thank you both. All right, maybe one or two more. Let's see. This question, I'm curious, both Owen and Nick, what you guys might think about this, but this is talking about having a mesh of DBT. So how does declarative automation work if you have a data mesh using DBT core? If you had dependencies that needed to run from another DBT project, would Dagster be able to cope with this?
I can speak to the mechanical aspect of that, which is yes. I think this goes back to an earlier answer. Essentially, it doesn't matter how those upstream dependencies are updated. Declarative automation will treat those updates the same, which really allows you to sort of like step back and like on each DBT model, you can just think about it in a vacuum. You don't need to worry about what the upstream team is doing exactly. You can just say, hey, I want this updated once a day, and leave it at that. But in terms of like the actual data mesh and that philosophically, I'm less familiar with that.
Yeah, I can pontificate on that. It's one of my favorite things. I guess, yesterday we talked about like us as a data platform. A lot of that is inspired by the data mesh, kind of the concepts there. I avoid the terminology a bit because it's a bit weird, to be honest, and unapproachable. But a lot of the core ideas are there for sure, in terms of, allowing practitioners to own, in this case, their data DBT projects end to end, and then us stitching that together in one coherent control plane. So I think that Dagster is like an ideal place to execute a mesh strategy.
Awesome, thank you. Well, there's still a couple of outstanding ones, but I think we're running low on time, so I think we'll call it there. As a reminder, you can hop on our public Slack at dagster.io/Slack, and if you have any questions, you're welcome to repeat them there, and we'll try to address them all in time. But thank you all for joining. Thank you, Stig and Tian, for being guests on this presentation. This was a super exciting one, and I look forward to seeing everyone tomorrow for the next day in Data Week.